One more example to computing frames and machines. We've got a frame here. This is problem 6.79 in another book. But the frame supports a 6 kilonewton load, which is right here, at C. And we're asked to determine the reactions on the frame at A and at D. So, I have taken the liberty already of drawing out each member. If I exploded the frame, took out the pins, and drew the free body diagram for each member. Let's go ahead and finish those. So I am going to say that AY and AX, I'm going to assume that AY is going up. AY is going to be going up, and AX is going to be going to the left. Now the reason I'm assuming that is this 6 kilonewton force is pushing this frame down, where the reaction here has to be pulling back so that it doesn't go down. And then dy and dx I'm going to do as typical, the way I do it. And then I'm going to go ahead and write down that BE, we'll say it's going to be acting this way. So this is also B, and this would also be E. And I'm going to go ahead and draw this like so. So this would be going in like so. So we actually know this is, we're going to call this BE. We're going to call this BE. So all these forces internally would also be BE. And over at C, I went ahead and drew them also. So all of these would be opposite and equal. This would be CF, 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 and CF. You also notice that I have all the dimensions drawn on the free body diagram. But something else that we may want to compute is this angle right here and this angle right here. So we'll call this alpha, we'll call this beta. Well, in order to calculate alpha and beta, let's look at the top frame up here. So if I kind of drew a dashed line right here, we know this is 0.5 meters because of this height here. But what is this dimension here? Well, if this is 0.4 to here, and this is 0.4 to here, and this is 1, so this would be 1.4, this would be 1.2, but this is half, so we want 1.4 to, or I'm sorry, 0.4 to here. This is 0.4, so 0.4 plus 0.4 is 0.8, so this whole thing is 1.2, so this would also be 0.4 from here to here. This dimension from here to here is going to be 0.2, 1.4 minus 1.2, and then we also have this as 0.5. So if we're solving for alpha, which we called this alpha, and we called this beta, alpha then would equal the arctangent of 0.5 over 0.4, and beta would be the arctangent of 0.5 over 0.2. So this comes out to be 51.3 degrees, and this came out to be 68.2 degrees. So we've got those. So this is actually going to be equal to 51.3, and this is going to equal 68.2 degrees. What I also like to do, like I did in the previous video, is I like to look at the entire frame and say, okay, I want to look at its forces here. We said, I'm actually going to erase both of those really quick. We said that AX is going to the left and AY is going up. And we said there that dx and dy would be as shown here. So if I sum my moment, and let's come over here and just put the whole frame. If we're analyzing the whole frame here, and I sum my moment at point A, I would get that dx times the 0.5 What you may have wanted to do is pause the video anytime I'm going to do something, try it, and then come back to the video. And then we're going to have this 6 kilonewtons, minus 6 kilonewtons, times the distance, which is this whole distance up here, which would be 1.4 meters. Now that's going to equal 16.8 kilonewtons. So we know that dE here, dx, is 16.8 kilonewtons. I'm just going to go ahead and label these down here as well. So by summing my forces in the y then, if I sum my, I sum my forces in the x, because this we have dx, now ax. So we know that negative ax, because we're saying, or I assume that it was going to the left, plus dx was 16.8 kilonewtons, that ax is going to also be 16.8 kilonewtons, but we assumed correctly because it's positive, so this is actually going to the left, just like we assumed, at 16.8 kilonewtons. So I can look at one of these members and I can figure out what I'm going to solve for. So if I looked at, let's look at this member up here. I have two unknowns here, and I have two unknowns here, BE and CE and D. So what I could do, let's take a look. If I sum my moment about point A right here, so we're looking at member A, B, C. So if I sum my moment at point A, so my moment at point A, I have BE, which is going to be negative, because this is going to be rotating around in a clockwise fashion. That's going to be, we'll put the distance first, times the force, which is BE, and that's going to be the sine of 51.8 degrees, minus 1.4 times the sine of 68.2, which is times CF. So we're multiplying CF now, and that's 68.2. And then we're going to subtract this 6 kilonewtons times the full distance, which was 1.4 meters. And that's all equal to 0. Now I'm going to go ahead and sum my moment at point, let's see. If I came back down here, let's say I did this. If I come down here and sum my moment about point D, so I look at member DEF. So remember, I'm trying to find two equations with the same two unknowns. So if I sum my moment about point A here, I get CE, or BE and CF. If I do the same thing here, I'll get the same two unknowns, and I could use two equations and two unknowns to solve for them. So let's go ahead and sum my moment about point D, and say BE times the sine of 51.3 times 0.8, which is its distance from here to here. And remember, we're just looking at the y component for this because the x component goes through this point, plus CF times the sine of 68.2, and that's the distance of 1.12. It's 0.8 plus 0.4. And there's nothing else here, so that's just going to equal to 0. So if I look at this equation here and I rewrite it, I'd get 0.312, which is negative, times BE, minus 1.29 CF. And I take this over to the other side, I'd get 8.4. And the second equation here, I'm going to rewrite right here, which would be 0.625, this here, sine 51.3 times 0.8, plus 1.114 CF is equal to 0. Now I plug this into a matrix 2 by 2 on my calculator, and I come up with these two values. I get 20.2 kilonewtons, and I get negative 11.3 kilonewtons, meaning that CF is actually, its actual directions would be shown here in this darker purple color. Those would be its actual directions. So then I can come and I can look at summing my forces in Y, looking at this member again, ABC, so I'm going to go ahead and write that out again. Looking at member ABC, and sometimes it's nice to write these out so you know you can go back and look to see what you did. Sum my forces in the Y is equal to 0. I'm going to get the AY minus 20.2 times the sine of 51.3 plus 11.3 times the sine of 68.2. And that's all. Oh, I almost forgot my 6 kilonewtons. So minus 6 kilonewtons is all equal to 0. So AY, when I plug this into my calculator, I got 11.3 kilonewtons. It came up positive, so my assumption is correct of it going up. Now I can sum my forces in the Y. Now let's do this. I could sum my forces in the Y here, or I could just go back to the whole frame and sum my forces in the Y. So let's go back to the whole frame. If I go back to my whole frame, I just calculated AY, I need DY, and then I have this external force of 6 kilonewtons. So I had to have my sum my forces in the Y. And I have 11.3 kilonewtons, positive, it's going up, minus 6 kilonewtons, plus dy. It's all equal to 0. So dy then is actually going to be equal to 5.28 kilonewtons. Now let me see something real quick. So 11.36, that comes out to 5.3, but it's going to be negative, so dy is actually going to be going down. dy is actually going to be going in a downward position here, which kind of makes sense to me. Might want to analyze it yourself, see if you agree. If you don't, we can get online and take a look at this to see what questions you have. So really, it's asking for A and D, so here's AX and DX, and then AY and DY. Those would be your final answers there. So I hope this example helps. Get online, discussion pages, and make sure that you're asking questions.